Okay, dear student, today we will take 18th lecture for Raman spectra. Physics paper number PH 5502. As you in the last lecture, in lecture 17, we have discussed the classical theory of Raman effect. In lecture 17, means in the previous lecture, we have discussed the classical theory of Raman effect. In this lecture, today we will discuss the fourth article. Today we will give the quantum explanation of Raman effect. Quantum explanation. Quantum explanation of Raman. So, in the previous lecture number 17, we have discussed the classical theory of Raman effect. Okay. Today, in lecture number 18, we will discuss the quantum explanation of Raman effect. That why we are getting Rayleigh line, Stokes line, and anti-Stokes lines. Okay. Okay, you know the nature of Raman spectra. Contains three types of lines. Raman spectra having three types of lines. One is the Rayleigh line. Another the Stokes line and anti-Stokes line. This thing we have discussed. So this is Stokes line. This is anti-Stokes line. Okay, so in the Raman spectra of scattered light, when the incident light beam or the strong visible beam of when the strong beam of visible ultraviolet light is scattered by the molecule, okay, in the spectrum of the Raman spectrum of scattered light, we are getting three types of line. One is the Rayleigh line, having same frequency as that of the incident beam. Okay, Rayleigh line having same frequency as that of the incident beam. Then one is the Stokes line, Raman line, having frequency less than the frequency of the incident light. Okay, and we also get anti-Stokes line having frequency greater than the that of the incident light. So we are getting three types of line: Rayleigh line or exciting line having the same frequency as that of the incident light beam. The Stokes Raman line having frequency low frequency, we are having frequency less than the frequency of incident light, and we get anti-Stokes line having frequency greater than the frequency of incident light. Similarly, you can say for wave number, the wave number of Rayleigh light is nu, the wave number of Stokes line will be nu minus delta, and wave number of anti-Stokes line will be nu plus delta. So delta nu, this delta nu is the wave number displacement from the Rayleigh line. Delta nu is the wave number displacement of Stokes line and anti-Stokes line from the Rayleigh line. Now we give the quantum explanation of these three lines, that why we get Rayleigh line, Stokes line, and anti-Stokes line. Okay. So first we explain that in Raman spectra why we get a Rayleigh line of the same frequency as that of the incident light beam. Okay. Then we will discuss about Stokes line having less frequency and anti-Stokes line having higher frequency than that of the incident light beam. Okay. Now I consider the two energy states of the scatterer molecule, right? I consider two energy states of the scatterer molecule. This is the lower energy state, which is the energy of the molecule is E double dash. This is the upper state, the energy of the molecule is E dash. I am giving the explanation of Rayleigh line. Why we are getting the Rayleigh line having the same frequency as that of the incident beam. Okay. So let us consider two energy states of the scatterer molecule. This is the lower energy state of the molecule in which the energy of the molecule is E double dash. This is the upper energy stationary state of the molecule in which the energy of the molecule is double dash. Right. And this is our scatterer molecule, right? This is a scatterer molecule. Okay, so I have shown the lower stationary energy state of the molecule, E double dash, okay, and upper stationary state of the molecule in which the energy of the molecule is E dash. So I have shown two states of the scattered molecule: lower energy state of the molecule in which the energy of the molecule is E double dash, and upper energy state of the molecule, E dash, in which the energy of the molecule is E dash. And this is the scattered molecule which is in the lower state. Now, what will happen when a light photon is incident on this scattered molecule? Incident light photon. The energy of the incident light photon is Hc upon lambda, right? So let us incident a light photon. Let us incident a strong, because you know in what happens in the Raman spectra that when a strong beam of visible or ultraviolet light, okay, collides with the scattered molecule, the light is scattered in different directions. Okay, so let us incident a light photon of energy is equal to Hc upon lambda. Now what is this 1 upon lambda is called? 1 upon lambda is called wave number mu. So you can also write the energy of the incident light photon is equal to Hc upon lambda, but 1 upon lambda is called the wave number. So you can also write the energy as Hc, because 1 upon lambda is called wave number. So energy of the incident light beam, energy of the incident light photon is Hc upon lambda, or Sc and 1 upon lambda is called wave number, Sc nu. Okay. Now, if the molecule is in the lower energy state E double dash, what is the total energy of the system? That the molecule, scattered molecule is in the lower energy state in which its energy is E double dash plus the energy of the incident light photon will be Sc upon lambda or Sc nu. So total energy of the system E double dash plus Sc nu will be conserved. Okay. So now we will give the quantum explanation of this effect. Okay. So according to yes. Now what will happen when the incident light photon is colliding with the scattered molecule, which is in the lower energy state E double dash, then after the collision, the photon is scattered. But if the collision is elastic, there are two types of collision: elastic collision and inelastic. In elastic collision, what happens? When the incident light photon having energy Sc upon lambda Sc nu collides with the scattered molecule in the lower state E double dash, then after the collision, photon is scattered with same energy. Scattered photon with same energy. What was the energy of the incident light photon? The energy of the incident light photon was Sc upon lambda or Sc nu. Then after the collision with the scattered molecule, photon is scattered with the same amount of energy, that is Sc upon lambda or Sc nu. Means the energy of the photon is not going to change after scattering. After scattering, the energy of the scattered photon remains same as that of the energy of the incident photon. So the energy of the incident light photon was Sc upon lambda or Sc nu. After collision with the scattered molecule, the photon is scattered, but in elastic collision, the energy of the scattered photon is not going to change, it remains same. There is also SC level or SC level. Okay, so this gives, okay, and molecule remains in the lower state. Molecule remains in the lower state after the collision. So this gives rise to a Rayleigh line. This gives rise to a Rayleigh line of the same frequency as that of the incident. So we write a small explanation for this. According to quantum explanation, okay, we give the explanation for that. According to quantum explanation, according to quantum explanation of Raman effect, according to quantum explanation of the Raman effect, according to quantum explanation of Raman effect, when incident light photon, when an incident light photon of energy SC upon lambda or SC mu, when a incident light photon, when a incident light photon having energy SC upon lambda or SC mu collides with scattered molecule, collides with scattered molecule, collides with scattered molecule, in the lower state interval dash, molecule is in the lower state interval dash, the total energy of the system, what is the total energy of the system? What is the energy of the scattered molecule in the lower state? E double dash, plus what is the energy of the incident light photon? SC upon lambda or SCB. So this total energy of the system, total energy of the system E double dash plus SC upon lambda SCB is conserved. Is conserved, right? So you must understand that when, according to the quantum explanation of Raman effect, when an incident light beam of visible altered light, okay, when an incident light photon having energy SC upon lambda or SC nu collides with the scattered molecule in the lower energy state E double dash, okay, the total energy of the system of molecular incident light photon will be E double dash plus SC upon lambda SC nu is conserved. Okay. Now there are two types of collision. Elastic collision and inelastic collision. If we consider elastic collision, now there are two types of collision as I discussed: elastic collision and inelastic collision, right? So if the collision is elastic, so there is a collision between incident light photon and molecule, okay? If the collision between incident light photon of energy SC upon lambda SC nu with the scattered molecule is elastic, then what will happen? After the collision, photon is scattered with the same energy. Okay, and molecule will remain in the lower state. Okay, it is not going into the upper state, right? So if the photon is scattered with the same energy, the energy of the scattered photon is not going to change, then this scattered photon will give rise to a Rayleigh line whose frequency is same as that of the incident beam. So we write that explanation. The collision is elastic. If the collision is elastic, it's the collision between Collision between incident light photon, collision between incident light photon and molecule is elastic. The molecule remains after the collision. Molecule is not going to the upper state. Molecule remains in its lower state equal dash, and molecule after the collision of incident light photon with the scattered molecule, the molecule remains in the lower state equal dash, but photon is scattered with the same energy, and photon is scattered with energy unchanged. Means you can say that photon is scattered with same energy as that of the incident. What was the energy of the incident photon? That was SC upon lambda or SCV. And after collision occurred with the scattered molecule, the photon is scattered with the same energy. So the energy of the incident photon is SC upon lambda or SC nu, and energy of the scattered photon is also SC upon lambda or SC nu. So photon is scattered with energy unchanged, or photon is scattered with same energy, and it gives rise to the Rayleigh light. At wave number 1. This is the explanation of Rayleigh line. That how do you get the Rayleigh line in this experiment? That when a incident light photon having energy SC upon SC nu collides with the scattered molecule, and if the collision between the incident light photon and scattered molecule is elastic, then after collision molecule remains in the lower state equal dash, it is not going to the upper state, and after collision molecule remains in the lower state equal dash, and photon is scattered with the same energy. That was the photon is scattered with its energy unchanged. The photon is scattered with the same energy. Means if the energy of the incident light photon is SC upon lambda or SC nu, the energy of the scattered photon remains same. It is also SC upon lambda or SC nu. And if the photon is scattered with the same energy, the energy of the scattered photon is unchanged, then this scattered photon whose energy is unchanged, okay, it will give a Rayleigh line at wave number nu. Okay, and that is why the frequency of the Rayleigh line is same as that of the frequency of the incident wave. Okay, and then we will explain Stokes-Raman line. Second explanation we will give. We have explained the Rayleigh line. Now we will give the explanation of Stokes-Raman line. Okay, so now we will give the explanation of Stokes-Raman line. Okay, you know very well the Stokes line having less frequency or less wave number, okay, and anti-Stokes lines having higher wave frequency or higher wave number. Okay, so we'll give the explanation of Stokes. That why we get Stokes line having less frequency or less wave number than the wave number or frequency of Rayleigh line. Okay, now what happens in the second type of collision when an incident light photon of energy SC upon lambda or SC nu collides with the scattered molecule in the lower state equal dash, this scattered molecule will absorb delta E energy from the incident energy. Molecule absorbs delta E energy from incident photon. and goes to higher state E dash. Okay. So initially your molecule is in the lower state E double dash. Now our incident light photon of energy Sc upon lambda or Sc nu is colliding with the scattered molecule. So this scattered molecule will absorb. The scattered molecule will absorb delta E energy. Scattered molecule will absorb delta E energy from the incident photon. Okay, and it goes from lower state E double dash to the upper state E dash. Now can you tell me? What is the energy of the scattered photon? Energy of scattered photon. Please think and tell me what is the energy? What is the energy of the scattered photon? Okay, before collision, what was the energy of the incident photon? Before collision, the energy of the incident photon was Sc upon lambda or Sc. Now, out of the energy Sc upon lambda or Sc nu, this molecule, this scattered molecule absorbs delta E energy. This scattered molecule absorbs delta E energy from the energy Sc nu of the scattered molecules and goes from lower state to upper state. So this incident light photon loses the energy delta E because the delta E energy is absorbed by the scattered molecule and it goes from lower state to upper state. So the scattered molecule loses delta E energy. So energy of the scattered photon will be Hc minus delta E. Right? Because when a light photon of energy Sc upon lambda or Sc collides with the scattered molecule in the lower state double dash, the scattered molecule absorbs delta E energy from Sc, right? So the scattered molecule absorbs delta E energy from the energy of incident light photon and goes from lower state double dash to upper state dash. So when photon is scattered, its energy will be less. Okay. Before collision, the energy of the incident light photon was Sc nu. Now from the energy Sc nu, the scattered molecule absorbs delta E energy and goes from lower state to upper state. So the energy of the scattered photon will be Sc nu minus delta E because delta E energy of the incident light photon is absorbed by the scattered molecule. Okay. So energy of the scattered photon will be less Sc nu minus delta E. So that explanation we write here. The collision may however be inelastic. So now we are talking about inelastic collision. The collision may however be inelastic when there is exchange of energy when there is a exchange of energy between incident light photon and molecule. See, in the first case, in the case of Rayleigh line, as we have discussed, there is no exchange of energy between incident light photon and molecule. But in the collision, however, in inelastic collision, there is an exchange of energy between incident light photon and molecule. Okay. The molecule loses the energy delta E. And incident light photon, light photon of energy, incident light photon having energy Sc upon Sc nu collides with the scattered molecule in the lower state. Okay, the delta E energy of the incident light photon is absorbed by the scattered molecule and goes from lower state to upper state. Now, delta E energy of the incident light photon is absorbed by the scattered molecule to go from lower state to upper state. The energy of the scattered photon will be less. That is H nu Sc nu minus delta E. So when incident light photon having energy Sc upon lambda Sc nu collides with the scattered molecule in the lower state double dash, the scattered molecule absorbs delta E energy from the incident light photon and goes from lower steady double dash to upper steady dash, so that the energy of the scattered photon will be less, Sc nu minus delta E, because delta E energy of the incident photon is absorbed by the scattered molecule. So when photon is scattered, its energy will be less than delta E. So energy of the scattered photon will be Sc nu minus delta E. Okay, so that will be right here. Then we write energy of scattered photon. Energy of scattered photon is Sc nu minus delta E, because out of the energy Sc nu of the incident light photon, delta E energy of the incident light photon is absorbed by the scattered molecule to go from lower state to upper state. So the energy of the scattered photon will be less than delta E. So Sc nu minus delta E. Okay. So we write the explanation of this. The molecule in the molecule in the lower state E double dash. The molecule in the lower state E double dash takes or absorbs delta E energy, from incident photon, right? The molecule, you can see the scattered molecule initially in the lower state E double dash, scattered molecule initially in the lower state E double dash absorbs delta E energy from the incident light photon. Okay? The scattered molecule initially in the lower energy state E double dash absorbs delta E energy from the incident photon and goes to and after absorbing delta E energy from the incident photon, it goes from lower state to upper state. So and molecule goes to a higher state E double dash. Sorry, E dash. Okay. So I think you can understand this sentence. The scattered molecule initially in the lower energy state E double dash absorbs delta E energy from the incident light photon and goes from lower energy state E double dash to upper energy state E dash. Okay. Therefore, photon is scattered. Therefore, photon is scattered with a smaller energy. Photon is scattered with a smaller energy, that is Sc nu. Was the energy of the incident light photon before the collision. Sc nu is the energy of the incident light photon before the collision. The energy of the incident light photon was Sc nu. When this light photon of energy Sc nu collides with the scattered molecule, the scattered molecule absorbs delta E energy from the incident light photon and goes from lower state to upper state. Therefore, the energy of the scattered photon will be small. Energy of the scattered photon will be Sc nu minus delta. Because from Sc nu energy of the incident light photon, the scattered molecule absorbs delta E energy and goes from lower state to upper state. Therefore, energy of the scattered photon will be Sc nu minus delta E. So, photon is scattered with a smaller amount of energy, Sc nu minus delta E. If the energy is small, photon is scattered with smaller amount of energy, wave number is also small. So this gives rise. Okay. So due to this scattered photon, we will get a Raman line whose frequency is less, wave number is less, right? So which is known as Stokes Raman line. So this gives rise to a this gives rise. This gives rise to a Raman line. This gives rise to a Raman line. This gives rise to a Raman line with the frequency less than that of the incident spectral line. Wave number. So this gives rise. This phenomena. In this E plus C collision, the photon is scattered with a smaller amount of energy, SC nu minus delta E. It gives rise to a Raman line, which is known as Stokes line, whose frequency or wave number is less than that of the incident line. Okay. So at what wave number we get this Stokes line that we calculate. Now we know the equation of wave number E is equal to SC upon lambda. Energy equation is SC upon lambda. The equation of energy is SC upon lambda. So 1 upon lambda is equal to what do we write? E upon SC. Right? What is this 1 upon lambda is called wave number nu. So wave number nu is equal to E upon SC. Okay. So this is the basic equation. You know that energy equation is SC upon lambda. Energy equation is SC upon lambda. So wave energy equation is SC upon lambda. So from this equation, wave number 1 upon lambda is E upon SC. Wave number 1 upon lambda is called E upon SC. Calculate the wave number of this Stokes line. So wave number of Raman lines is equal to E upon SC. E upon SC. Now you know the energy of the scattered photon. Energy of the scattered photon. What was the energy of the scattered photon? Because the before collision, the energy of the incident light photon was SC upon SC nu. Okay, when this light photon collides with the scattering molecule, the scattering molecule absorbs delta E energy from the energy of incident light photon SC nu and goes from lower energy state equal dash to higher energy state dash. Okay, so out of the energy SC nu, the scattering molecule absorbs delta E energy and goes from lower state to upper state. Therefore, the energy of the scattered photon will be SC nu minus delta E, right? Because the before collision, the energy of the incident light photon was SC nu. The scattering molecule absorbs delta E energy from the energy of the incident light photon and goes from lower state to upper state. Therefore, the energy of the scattered photon will be less. The photon is scattered with smaller amount of energy, SC nu minus delta E. Because why the energy of the scattered photon is small? Because from energy SC nu, delta E energy is absorbed by the scattered molecule and it goes from lower state to upper state. Okay. So now we put here the energy of the scattered photon is SC nu minus energy of the scattered photon is SC nu minus delta E upon SC. Therefore, you will get wave number is equal to SC cancel nu minus delta E upon SC. Okay. So you will get this line. Okay, the wave number of this line is nu minus delta E upon SC. So wave number of this Raman line is less than the original wave number nu of the incident line. So what was the wave number of the incident line? The wave number of the incident line was nu, but wave number of this Stokes line is nu minus delta E upon SC. So wave number is less. Such a Raman line such a Raman line is called such a Raman line is called Stokes line. Right? Such a Raman line is called a Stokes line whose wave number is less than the wave number of the incident light, nu minus delta A over SC. What is the wave number shift? What is the wave number shift? You can see here the wave number shift delta nu is equal to delta A upon SC. So wave number shift delta nu is delta A upon SC because nu is the original frequency or wave number of the incident light, and wave number of the Stokes line, is nu minus delta A upon SC. So wave number shift is delta A upon SC. So wave number shift is wave number shift of Stokes line is delta A upon SC. So wave number of the Stokes line is delta A upon SC less than the wave number of the Rayleigh line. If the wave number of the Rayleigh line is new, then wave number of the Stokes line will be nu minus delta E upon SC. Right? If the wave number of the Rayleigh line is new, then wave number of the Stokes line is nu minus delta E upon SC. So wave number shift of the Stokes line from the Rayleigh line is delta E upon SC. So this delta E upon SC is the wave number shift of the Stokes line from the Rayleigh line. And finally, we give the explanation. Finally, the explanation of anti-Stokes Raman. So we get Rayleigh light when photon is scattered with the same energy. When photon after collision with the scatter molecule, when incident light photon is scattered with the same energy, we get a Rayleigh line at wave number nu. Okay. When photon is scattered with smaller energy, when photon is scattered with smaller energy, you will get a Stokes line whose wave number is nu minus delta A upon SC. So wave number shift from the Stokes Rayleigh line will be delta A upon SC. And now we will give the quantum explanation that why we get a anti-Stokes line. Why we get an anti-Stokes line. Okay, so for that, again we consider the upper state of the molecule, E dash. This is the lower state. Energy state of the molecule is the energy of the molecule is E double dash. And now scatterer molecule is not in the lower state, but we consider that scatterer molecule is in the upper state. This is the scatterer molecule is in the upper state. Okay, so now when is the incident photon, energy is SC upon lambda or SC nu. Okay. Now when the incident light photon, incident photon whose energy is SC upon lambda or SC nu. Okay. Now if the molecule initially in the upper state E dash, okay, and the incident light photon of energy SC nu collides with the molecule in the upper state E dash, the molecule comes back to the lower state E double dash. Okay, What is delta E? Delta is the difference of energy between two states, E dash minus E double dash. Okay. Then the photon is scattered after collision with the after collision of the incident light photon, after collision of the incident light photon with the scattered molecule in the upper state E dash. Okay. What will happen? The molecule comes back into the lower state E double dash. Okay. But what is delta E? It is the difference of energy between upper state E dash and lower state E double dash. The photon is scattered. The energy of the scattered photon energy of scattered photon. Yes. Before collision, what was the energy of incident photon? Sc nu. Sc nu. Sc nu. Now, what will happen when a light photon of energy Sc nu collides with the scattered molecule in the upper state E dash? Okay. The light photon will absorb delta E energy. Light photon will absorb delta E energy, and scattered molecule comes back from upper state to lower state. Okay. Scattered molecule will come back to the from upper state to lower state, and this incident light photon will absorb this delta E energy, and when photon is scattered, its energy will be Sc nu plus delta E. So the energy of the scattered photon is increased. Okay. In the previous case, photon was losing the energy delta E, so photon is scattered with smaller amount of energy Sc nu minus delta E. Now in this collision, photon is gaining delta E energy, so photon is scattered with energy Sc nu plus delta E. Okay, so on the other hand, so we also mentioned this. On the other hand, the molecule was initially the molecule initially in higher state E dash is transferred to lower state E dash, by collision. Right? On the other hand, the molecule initially in the higher energy state E dash, when collides with the incident light photon, okay, molecule come back to the lower state E double dash. Molecule is transferred to the lower state E double dash by collision. Okay, so when molecule is transferred from upper state dash to lower state double dash, its delta E energy, okay, is absorbed by the scattered photon. So the photon is scattered with a large amount of energy, Sc nu plus delta E. So when molecule is transferred from upper energy state dash to lower energy state double dash, the energy of the scattered photon will be Sc nu plus delta E. So that I will also mention here. Therefore, the energy of scattered photon is now Sc nu plus delta E. Energy of the scattered photon will be Sc nu plus delta E. So in the previous case of Stokes-Raman line, the photon was losing the energy delta E, so photon is scattered with smaller amount of energy Sc nu minus delta E. In this case, photon is gaining delta E energy, so the energy of the scattered photon will be large, that is Sc nu plus delta E. So when a light photon and the light photon of incident light photon energy Sc nu collides with the scattered molecule in the upper state E dash, okay, the incident light photon will absorb delta E energy. The incident light photon will absorb delta E energy. Okay, in the previous case, photon was losing the energy delta E, right? In the previous case, photon was losing the energy delta. In this case, the incident light photon having energy S nu, when collides with the scattered molecule in the opposite radius, this light photon, incident light photon will absorb the energy delta E, which is equal to the difference of two energies, radius minus radius. And if the incident light photon absorbs the energy delta E, then the photon, the scattered molecule, is transferred from upper state dash to lower state equal dash, and photon is scattered with a great amount. Photon is scattered with larger amount of energy, that is C plus delta E. So in the previous case, the energy of the scattered photon was S C minus delta E. In this case, the energy of the scattered photon is S C plus delta E. So when the incident light photon having energy S C nu collides with the scattered molecule, incident light photon of energy S C nu collides with the scattered molecule in the upper C dash, the molecule is transferred from upper C dash to lower C equal dash, and photon is scattered with large amount of energy S C nu plus delta E. So whatever the energy lost by the scattered molecule is gained by the photon. So in this case, in this condition, photon is gaining the energy delta E. So energy of the scattered photon is delta E. Okay. So now the energy is more, so wave number will be more. So that gives rise to the anti-Stokes line whose wave number is more than the wave number of Rayleigh. So now we will calculate the wave number due to this scattered photon. We will calculate the wave number of this anti-Stokes line, which is obtained due to the large amount of scattered photon, that is C plus delta E. So this gives rise to a Raman line. This gives rise to a Raman line whose frequency is greater. Whose frequency is greater. So this gives rise to a Raman line. This gives rise to a Raman line whose frequency is greater. Than that of incident spectral line. At wave number, right? So when the energy of the scattered photon is increased by delta E, it gives rise to a anti-Stokes line whose frequency is greater than that of the incident line. At wave number, so we calculate the wave number of anti-Stokes line. So wave number is equal to, you know very well, whenever you want to calculate the wave number, the procedure is this: you have to divide the energy of scattered photon by SC. So what is the energy of the scattered photon? Is SC plus delta E. As I told you, in case of Stokes line, the photon was losing the energy delta E. So the energy of scattered photon was SC minus delta E. In case of this anti-Stokes line, the photon is gaining the energy delta E. So energy of the scattered photon is SC plus delta E. SC plus delta E upon SC. Okay, so wave number of the anti-Stokes line is nu plus delta E upon S. Wave number of the anti-Stokes line is nu plus delta E upon S. So I write that here. The wave number of Stokes line was nu minus delta E upon S, and wave number of anti-Stokes line will be nu plus delta E upon S. So wave number 6 delta E is nothing but delta E upon S. Okay. So from a Rayleigh line, Stokes line is situated at delta E upon SC6. This is the wave number 6. Okay, and the wave number of Stokes line is nu minus delta E upon SC. Okay, and wave number of the anti-Stokes line is nu plus delta E upon SC. Okay, such a Raman line is called anti-Stokes line. Such a Raman line is called anti-Stokes line. Okay. So the wave number of Stokes line is nu minus delta E upon SC, and wave number of anti-Stokes line is nu plus delta E upon SC. Such a Raman line whose wave number is more, wave number or frequency is higher than the frequency of wave number of Rayleigh line is called anti-Stokes line. So in this way we have given the quantum explanation of Rayleigh line whose frequency of wave number is same as that of the incident line spectra, and the wave number of Stokes line is less, and wave number or frequency of anti-Stokes line is more than that of the incident line. We have given the complete explanation. Okay, you can see here that Stokes line and anti-Stokes lines both are situated symmetrically about the Rayleigh line. Wave number shift is delta E upon SC. So that we also mentioned. Thus, Stokes and anti-Stokes line, Stokes and anti-Stokes lines Stokes and anti-Stokes lines are symmetrically situated on either side of Rayleigh line. You can see that Stokes Raman line and anti-Stokes lines are symmetrically situated. Stokes Raman line and anti-Stokes Raman line are symmetrically situated on either side of the Rayleigh line. The Raman shift is returning is equal to delta E upon SC, right? So you can see here that Stokes Raman line and anti-Stokes Raman line, both lines, Stokes Raman line and anti-Stokes Raman line are symmetrically situated on either side of the Rayleigh line. Okay, and the Raman shift, wave number shift of Stokes line and anti-Stokes line from the wave number of Rayleigh line is delta E upon SC. What is this delta E? You should know what is this delta E. Is the energy difference of upper state and lower state. So this delta E is nothing but delta E is the energy difference of the molecule between the upper state and lower state. So in this way, we have given classical explanation of the Raman spectra, and we have also given the quantum explanation of Raman effect. Right? Both the explanations we have given. Now we have two types of Raman spectra. We have two different kinds of Raman spectra. We have two different types of Raman spectra. One is the vibrational Raman spectra, the second one is the rotational Raman spectra. So in the next lectures we will discuss these two different kinds of Raman spectra, that vibrational Raman spectra and rotational Raman spectra. Okay, I the vibrational Raman spectra of the molecule is obtained when molecule makes a transition from one vibrational level to other vibrational level. Okay, so next lecture we will take this, but just give the introduction of vibrational Raman spectra. The next article is vibrational Raman spectra. Vibrational Raman spectra. Suppose I have two vibrational levels. This is the lower vibrational state generated by quantum number variable dash, and this is the upper vibrational state nu dash. Both the states are belonging to the same electron. Both the states Both the states are belonging to the same electronic state. Okay. Now, when molecule makes a transition between lower vibrational state and upper vibrational state, we will get a vibrational Raman spectra. Both these vibrational states are belonging to the same electronic state. So, vibrational spectra is obtained when molecule makes a transition between two vibrational levels belonging to the same electronic state. So, when molecule makes a transition from one vibrational level to the other vibrational level belonging to the same electronic state, we get vibrational spectra. So, I mentioned that the vibrational spectra arises. The vibrational spectra arises due to the transition of molecule. So vibrational spectra arises due to the transition of molecule from one vibrational level state to other vibrational state belonging to same electronic state. So when molecule makes a transition from one vibrational state nu double dash to other vibrational state nu dash, okay, we will get the vibrational spectra. So vibrational spectra arises due to the transition of molecule from one vibrational state nu double dash to other vibrational state nu dash, and both these vibrational states belong to the same electronic state. For that, okay, we will give the quantum explanation. Okay, quantum mechanically, the origin of Raman lines can be explained by considering matrix element of scattering dipole moment. Okay, so according to quantum mechanics, the origin of Raman lines, that why we get Stokes line and anti-Stokes line, can be explained if we consider the matrix element of scattering dipole. So quantum mechanically, the explanation of Stokes Raman line, and anti-Stokes line can be explained by considering matrix element of scattering dipole. So I will write the equation of matrix element of dipole and then we will stop. Okay, we discuss that here in the next lecture. So I write the matrix element in this way. So matrix element of scattering dipole moment is given by R and M is equal to, you try to understand this equation, psi n star P is the dipole moment, psi n dipole, right? So this is the equation. Okay. You will study in quantum mechanics. You will study this equation in quantum mechanics. Please try to remember this equation, that the matrix element of scattering dipole moment denoted by R between two states N and M is defined by integral psi n star, p psi m d tau. Okay, I give the name of each. Okay. Now what is the psi n and psi? Okay, suppose I consider two states. Suppose this is the nth quantum state of the molecule. Then in the nth quantum state, actually n is nothing but nu dash. Right? Sorry. I give the name, the upper state nu dash, I give the name n. The lower state nu double dash, I give the state n. Okay. So in the upper state n, which is equal to nu dash, the wave function of the molecule is psi n or psi nu dash. Right. In the lower state n is equal to nu double dash, the wave function of the molecule is psi n is equal to psi nu double dash. Okay. So generally, what is psi n is equal to psi nu dash? Is the upper vibrational state of the molecule, and is denoted by vibrational quantum number nu dash, and the wave function of the molecule in the upper state is psi n or psi nu dash. The lower vibrational state of the molecule m is denoted by vibrational quantum number nu double dash, and psi m is the wave function of the molecule in the lower vibrational state m, which is psi nu double dash. Okay. So psi n is equal to psi nu dash is the wave function of the molecule in the upper vibrational state nu dash, and psi m is equal to psi nu double dash is the wave function of the molecule in the lower vibrational state nu double dash. Now what is this p here? P is the dipole moment. Dipole moment. As you know, the dipole moment P is proportional to E. So P is equal to alpha E. Right? So P is the dipole moment. I explained already R. Once again, what is R? R is the matrix element. R is the matrix element of scattering dipole moment. R is the matrix element of scattering dipole moment between two states n and m of the molecule. Okay. The psi m is the wave function. Psi m is the wave function of the molecule in the upper vibrational state nu dash. Okay. So you can write psi m is equal to psi nu dash. And what is psi m? Psi m is the wave function of the molecule in the lower vibrational state nu double dash. It is psi nu double dash. Okay. This P is the dipole moment. Dipole moment is directly proportional to E. So P is equal to alpha E. Okay. What is this alpha? Alpha is called polarizability. This is alpha. Alpha is called the polarizability. This alpha is called polarizability of the molecule. And this E is the oscillating electric field of the incident, right? So this alpha is called the polarizability of the molecule, and this polarizability of the molecule is varying due to vibrational motion of the molecule and rotational motion of the molecule. And E is the oscillating electric field or incident light. Which is equal to E0 sine omega, right? So the next lecture we put the value of dipole moment P is equal to alpha E. We put the value of dipole moment P is equal to alpha E in this equation, and we will calculate the matrix element. Next lecture we will calculate the matrix element of dipole moment between two vibrational states, n is equal to nu dash and m is equal to nu dash. Thank you so much. We stop here.